The Hopcroft Karp algorithm is an algorithm for finding a maximum cardinality matching on a bipartite graph. It can be used to solve problems such as assigning a set of jobs to a set of machines of varying capabilities so that as many machines as possible are being used. The algorithm works in a bipartite graph consisting of vertex sets U and W by taking a partial matching M, initially empty, and finding an augmenting path P that starts at an unmatched vertex in U, ends at an unmatched vertex in W, and alternates between unmatched and matched edges. The symmetric difference of M and P is then a partial matching of size 1 larger than M. The algorithm runs in phases. In each phase, a breadth-first search is run starting from the unmatched vertices in U to find the complete set of shortest possible augmenting paths. The breadth-first search marks the distance of each vertex visited. Once all of the shortest possible augmenting paths are found, a depth-first search is run starting from the unmatched vertices in U and ending at unmatched vertices in V, following only edges found by the breadth-first search where the distance of the target vertex is 1 plus the distance of the source vertex. These restrictions ensure that a maximal disjoint set of shortest augmenting paths is chosen. Once this set is found, we take the symmetric difference of the partial matching M with the edges in this set to find a new partial matching. The algorithm terminates when the breadth-first search finds no augmenting paths. Consider this example. In the first phase, each edge is an augmenting path, so we can choose any maximal vertex disjoint set of edges to add to our partial matching. In the second phase, we start our breadth-first search from the free vertices in U. We follow unmatched edges from these vertices to vertices in W, then follow matched edges back to U, repeating until we find free vertices in W. Once we have found all the paths of the length of the shortest augmenting path, in this case 3, we stop the breadth-first search and use a depth-first search to pick a vertex disjoint set of augmenting paths. In this case, we pick 2 paths. Taking the symmetric difference of these 2 paths with the partial matching gives us a new partial matching. In the third phase, we again search for augmenting paths, finding the first one at depth 5. We also find a path of length 5 to a matched vertex, F, which is not a valid augmenting path. In the fourth phase, the breadth-first search finds no augmenting paths, so the algorithm terminates. The Hopcroft Karp algorithm runs in big O of e square root of v time. Each breadth-first search takes big O of e time, as it visits each edge at most once. Similarly, each depth-first search takes big O of e time, so each phase takes big O of e time. The algorithm terminates in big O of square root of v phases. To show this, we need the following lemma, stated without proof. After a phase where the shortest augmenting path was of length k, the new shortest augmenting path is of length at least k plus 1. Now consider the state after square root of v phases. At this point, we have a partial matching M. If we take the symmetric difference of this matching with a maximum cardinality matching M prime, we get a set of disjoint augmenting paths and cycles. By the lemma stated, the augmenting paths are of length at least square root of v, so there can be at most square root of v of them. Each augmenting path increases the size of the partial matching by 1, so the difference in size between our partial matching and a maximum cardinality matching is at most square root of v. Since each phase finds at least one augmenting path, each phase increases the size of the matching by at least 1, and there can be at most square root of v more phases before a maximum cardinality matching is reached, giving at most 2 square root of v phases. The time complexity of the Hopcroft Karp algorithm is thus big O of e square root of v.